graph to identify the following values. So first of all, this is a velocity versus time graph. It's really important to check the axes and make sure you understand that these values are your velocities. Positive values mean moving forwards. Negative values mean moving backwards. So again, positive and negative values don't mean less than or greater than 0. They mean forward versus backwards. So using this information, this is a Pasco capstone graph with labeled coordinates and all that. So we're going to use this. So here's point A's time. And here's point B's time. And here is point right here. And here's point C's time. And then the velocity at A is going to be this value. At B is this value. And at C, we've got negative 0.603. Acceleration is going to be the slope of a VT graph, right? So the slope is given in the equation of the line. M is the symbol for slope in this case, so we've got negative 0.376 meters per second squared. The delta t is going to be the change in time, so it's going to be 2.20 minus 0.450. So 2.2 minus 0.45 is 1.75 seconds, and then doing the same thing, B to C is 1.90. Displacement is going to be the area under the curve. That's one way to do it. So you could take this area, right, and calculate it. So the area is going to be the two triangles. So we could do this time frame, which is 1.75, times the height, which is 0.734. And then the second area, the second region time, we figured out is 1.9. And this height, quote unquote, right, it drops below, so you need this velocity at C, which is negative. So let's calculate that. So it's 0.5 times 1.75 times 0.734, and that's going to be 0.642, and the other one's going to be 0.5 times 1.9 times negative 0.603, and we get negative 0.573. So then to finish, plus that answer to, add that answer to the first term, and you get 0.069. So you've almost come back, to where you began, right? If you've moved forward for this section and then backwards for this section, that's what that means. You're going back towards your origin. But you're still a little bit ahead, not by much. The distance traveled is going to be the absolute value of these segments, right? The total distance here and the total distance here without dealing with the negatives. So you would do 0.642 plus 0.573, which would give you 1.22 meters would be your distance traveled. So what could be happening here? So to make up a little story, I might say there's an object, it increased its speed, it was maybe given a push until it reached a speed of 0.734, and then it slowed down with a constant acceleration. So maybe it was going up an incline, right? So it was slowing down up that incline. It stopped for a brief moment at 2.2 seconds, and then it increased pretty much at the same rate, going back down that incline until it returned to the bottom. So it would look like, here's the car, someone gave it a shove up the incline and then allowed it to roll, and it decreased speed on the way up, and then, right, it it started moving back down and it increased speed on the way back down where this was the 0 position. That make sense? Okay, number 5, this set of questions. The graph shows the velocity of 2 runners racing on a track. At time t equals 0, both runners are located at the starting line. Runner 1 had a running start and moves at a constant velocity of vr1. So that's what's shown for the entire race. So here's the first guy right here. And then the second person, runner 2, is starting at rest and then goes at constant speed, right? So here they're accelerating, right, along this and then moving at a constant speed. So they had to start at rest. This guy was constant the entire time. So don't forget, this is a velocity time graph, not a position time graph, okay? So when, if ever, will runner 2 catch up to runner 1? Now, how do you tell if someone has caught up to somebody else? Well, they have to be at the same position at the same time. So when will they be at the same position? Well, look at this graph. If you want to find the displacement, right, you need the area under the curve for a VT graph. So look, this area, is it ever going to be the same as the other area, right, as this area, right? The yellow area is always going to be bigger by this amount. Even if this was infinitely big, this would still be a little bit bigger. So never, right? Runner 1 is always going to win. At time TR2, which is right here at this intersection, runner 1 has gone a distance d. By analyzing the motion of both runners, find the acceleration of runner 2 in terms of VR and d only. So you can't use that time in your answer. So let's figure it out, right? The acceleration of runner 2. So we know, let's make our normal, let's make a chart to try to figure out some of the stuff we know. This is for runner 2. So runner 2 has initial velocity of 0 and a VR1 is a given. So when they tell you express something, right, you want to just, that's a number. It's not really a number, right? But it's a number. You have to get it into your head that this is an actual given value, okay? We also know that at that point, right, at the time TR2, you have covered distance d. So these are given values, and this is what we want to know. So, actually, no, that's not true. Sorry. So this is runner 2. We don't really know anything else. We do know that runner 1, who goes at constant speed of VR1, has no acceleration, covers a distance d. That's a given value as well. Okay, and this is at TR2, TR2. So these are facts that we know. If we write this out as an equation, we know that velocity is constant speed is distance over time. So VR1 is d over TR2. So this TR2, we can actually rearrange this and get an expression for that time in terms of two given values. Right? These are both given, so you're okay leaving it like this. So now we, quote unquote, know what TR2 is. So if we want to find acceleration, we know acceleration is change in velocity over change in time. So the change in velocity is VR1, which is a given, minus 0, because for person 2, runner 2 starts at rest, and we have this time, d over VR1. So I can simplify this, and this is VR1 squared over D. And this is an expression for acceleration in terms of the given values. So that was number 5. 5B. Next, C. Describe and prove one thing runner 2 could change so that she could catch up to runner 1 at an earlier time. So what can you change if you want to get there earlier? If you want to make TR2 less, then you're going to have to either increase your speed, right? You have to get up, or you have to really, the only thing you can really do is increase your acceleration, okay? And that comes right out of that derivation here, right? Looking at this, if you want to do this in a get at an earlier time, that really means you want this number to be smaller, right? If this is smaller, that means you have to increase your acceleration. Okay. And then D, students in a physics class observing the race note that each runner must slow down to a stop after the race. This part's not shown in the graph. A student claims the acceleration of both runners must be negative as they come to a stop, but student 1 disagrees, saying that is impossible, right? Negative means the opposite direction is positive. So since the runners never move in a negative direction as they slow down, their acceleration is never negative. And so what about this is correct and incorrect? So negative does mean opposite direction is positive, right? That is true. So if the runners are moving in a positive direction, so their velocities are positive, if they want to slow down and decrease speed, acceleration must be negative. The sign of acceleration, right, does not denote direction of velocity. It just says the direction of the change in velocity. So this is so the part of this is true, but this part is not true. This is a ranking problem. So if we look at these 6 graphs, the first part, A, asks us to look at the distance traveled, and then part B asks for displacement. So let's do those 2 first. When you want to find distance or displacement as well, you need to find the area. So we're going to use the area of the VT graph because that'll give us the total distance traveled as long as we don't worry about the negatives, okay? So we're going to look at each one. We'll do A, B, C, D, E, and F, and then we'll rank them. So for the first one, the area is 1/2 times the time times that height, which is 8. The second one is 1/2 times the time times -8. And then this one is 1/2 times time times, right? We're going to go from 0 to -8. So we're going to go, and then we've got, oh, this one's not half. This is just 5 times 10. This is -5 times 10. This one is 1/2 5 times 10. So you can just run through the calculations. But for me, since they all have 10s in them, I wouldn't really bother worrying about it because I just need to rank them. So I would just do the 1/2 and the 8 because then I can, but it doesn't really matter if you want to just do this. This gives you -40, -40, 50, -50, and 25. So you can rank them, but here's the thing, with distance, we take the absolute value. So any of these negatives don't matter for distance. So then it becomes D equals E is greater than A equals B equals C, which is greater than F. But for displacement, the negatives do matter. So then it's the same calculation, but we get rid of those absolute value signs. So then we've got D is greater than A, which is greater than F, which is greater than B equals C, which is greater than E, because the negatives then do matter. The part C asks you to rank it in terms of average speed. So that's going to be, right, the average value, which is going to be 1/2 your initial and your plus your final. That's how you do averages in general. Again, the difference between average speed in C and average velocity for part D is going to just be a matter of signs, right? Using displacement versus distance. So you can actually calculate it using these values, but since the times are all the same, we know that speed is proportional to distance. So therefore, the ranking is going to be the same as the distance ranking. Oops. So that's, you don't even have to do anything. So always look for little things like that. For part D, since velocity is proportional to displacement, it's going to have its ranking the same as the displacement ranking, which is B. So you don't have to redo those calculations. E is asking about instantaneous velocity at 10 seconds. So now we kind of have to go back and take a look at what that velocity is at 10 seconds. So let's read the graph. Here, velocity is 0. Here, velocity is -8. Final velocity is 0. At 10 seconds, velocity is 5. Here, velocity is -5. And again, here, velocity is 0. So using that information, we can see that the biggest velocity is going to be this here, where it's 5, that's D. And that's greater than 0, 0, 0. We've got all those zeros. So A and C and F are all 0. And then we've got -5, which is greater than -8. So that would be your ranking for that. Then the last one asks you for acceleration. The acceleration is the slope of a VT graph. So we have to look at these slopes. So we've got here, the slope is going to be, right, change in velocity over change in time. Since the times are the same for all we got to look at is this change in velocity. So I'm just going to look at the change in velocity to make this determination. So it's 0 minus 8 is -8. This one is going to be -8 minus 0, which is again -8. This is going to be 0 minus -8, which is +8. This one's just going to be change in velocity is 0. This one, change in velocity is 0. This one is 0 minus 5, which is -5. So now when I want to rank these, I can look at those values that I just generated. So this +8 is the biggest one. So let me write it. I'm having a little trouble with space here. So with ranking, I'm going to say +8 is C is greater than +5, which is D, which is greater than 0, which is greater than -5, and then these two are both -8. So that would be my ranking for acceleration. So that was part F. The last question on this very long guided practice shows you yet another graph with 2 lines this time. So we've got a line for car X. And right away I'm going to say to myself, well, that's constant speed, right? Because it's not increasing or decreasing in value. This is starting at rest and increasing speed. And I can see this point of intersection here. This tells me when the speeds are the same. It doesn't tell me when their paths cross. Okay, this is when the speeds are the same. That's really important. A lot of us like just right away associate this with a position time graph, and they think when they intersect, they're actually going to be at the same place. But if you want to find where they are when they're at the same place, you need the area is displacement. When their areas are equal, then they will be at the same place. And they're never going to be at the same place because this area is always going to be, well, actually, they may at some point because this one is increasing. So you can actually calculate the area there. Anyway, what are they asking? What's true at time equals 20 seconds? At 20 seconds, Y is behind car X. Well, that's still true because the area, right, is displacement, and the area of Y at 20 seconds is less than the area of X at 20 seconds. So that's true. This is not true. We just talked about that. Car Y can't be in front because it hasn't yet passed it. It hasn't covered the same position. And Y is accelerating faster than car X. Well, that's true because car X isn't accelerating at all. So these two are both true statements. So you'd have to pick both of them.